Hello everyone, my name is Ishani Sarkar. I am here to present my paper on data-driven analysis and tuning of a live hybrid CDN V2V video distribution system. The typical architecture of the live video streaming uses either dynamic adaptive streaming over HTTP or HTTP live streaming protocol. For both the protocol, the stream is divided into smaller chunks. The clients first download the manifest file, which has the information about the small chunks, and then the smaller chunks are downloaded. One of the important challenges of live streaming is that it needs to be fairly synchronized with the live time. Also, the basic client-server architecture, where every request for each chunk is sent to the CDN, induces high bandwidth cost for the content provider. At EasyBroadcast, we use BARTC, which provides a clientless solution and allow different browsers to communicate between each other without any third-party software, and allows them to exchange video chunks. We call this V2V exchanges. It elevates the traffic from the CDN. At EasyBroadcast, we operate over 300 worldwide video and radio channels and have almost 27 million unique viewers. In this slide, I would like to present two of the important components of the EasyBroadcast architecture. The first important component is the video player, another is the EasyBroadcast library. So as you can see, as the viewer starts the player loads the EasyBroadcast library. It's the player who decides the playing quality of the stream, and it is the EasyBroadcast library who decides whether the chunk will be downloaded from the CDN or from another viewer. To explain a bit more in detail about the chunk download process, as we already know, the player loads the EasyBroadcast library. The EasyBroadcast library then queries the manager for other viewers who are watching the same content are in the same quality level. Viewers then connect with each other to form a swarm. Viewers download the video. First download tries to download the video from the swarm, and after TO seconds, it goes to the CDN. TO second depends on the chunk size of the stream. For example, if the chunk size is 6 seconds, we give 5 seconds to download in the V2V mode. Some of the challenges that we have tried to tackle in this paper is to increase the V2V efficiency, and also decrease the unsuccessful V2V chunks which are sent but are not received before the timeout, leads to unnecessary traffic in the V2V environment. In this paper, we have profiled a typical video channel. We then identify the bad client that shouldn't be uploading the chunks to the viewers, and then devise an algorithm to allow the clients to identify the viewers as bad. We have done the experiments in both controlled and the wild. One of the main constraints while creating this algorithm is to maintain the quality of experience for the viewers. We now, in the next section, we do channel profiling, we discuss the data set, and we also do some client profiling as well. We have aggregated over 3 days of data with over 34,000 unique clients, and almost 6.2 terabytes of data was downloaded. The analyzed channel is an entertainment channel along with some important sports event broadcasted over time. We collect various information in our data set, but the most important information that we collect is the exchange between viewers and CDN. We started our client profiling, and we saw that almost 1% of the viewers are doing 90% of the bytes exchanged in V2V mode. We correlated this with watching time. So for overall viewers, the mean watching time is almost 6 seconds, whereas for top 1% viewers, the mean watching time is 2 minutes. Another factor that is likely to heavily affect the viewer's ability to perform effective V2V exchanges is its network access characteristics. As part of the content is downloaded from the CDN servers, which is likely to be close to the client and feature good network performance, the average throughput achieved during chunks download from the CDN provides a good hint on the network access capacity of the users. As we can see from figure 1, there is a significant difference between the CDN bit rates of the overall viewers and the most active top 1% viewers, which experience way higher throughputs. The correlation coefficient between CDN bitrate and the chunk loss rate for overall viewers is minus 0.47, whereas for the most active top 1% viewers, it is minus 0.7. Ideally, when we do expect these values to be negative, as better the access length of the user is, less likely it is to miss the deadline while sending or receiving a chunk. For this perspective, the CLR is highly correlated with the CDN throughput performance, and it thus is a good metrics to and thus it is a good estimator for the reception quality of the viewers. The actual chunk loss rate of the overall viewers and the most active viewers are represented in figure 2. As we can see, for the top 1% viewers, the graph is left skewed. Over almost 50% of the clients experience less than 20% loss chunk rate, whereas all the other viewers experience uniformly between 20% and 75% loss chunk rate. We further move forward and we divided the top 1% viewers into good viewers and bad viewers. The good viewers, we did this just to isolate some of the important causes behind high chunk loss rate. And now we would now do the detailed analysis and test different hypotheses behind high chunk loss rate. The first hypothesis states that the neighbor set size of the viewer should affect the chunk loss rate, but from our analysis, we did not find any significant correlation between the CLR and the song size. The next hypothesis was the type of device play a role in the chunk loss rate. We again did not find any significant correlation between the type of device and CLR. We have further discussed both the hypothesis in detail in the paper. I would like to now focus on the last and the most important hypothesis. The last hypothesis is the network uplink and downlink throughput affects the loss chunk rate. As you can see from figure 5 and figure 6, good viewers have good CDN and V2V throughput, whereas bad viewers have reasonable CDN and poor V2V throughput. Hence, the bottleneck is the uplink capacity of the users. We use this to create an algorithm to identify bad clients. We call this algorithm a CLR mitigation algorithm. The overall logic behind this algorithm is that the viewers estimates its chunk loss rate when sending. If it is too high, the viewers stop uploading chunks to the other viewers, but they can still download in V2V mode. They stopped uploading the chunks for some time. There are more details for this algorithm discussed in there. More details about this algorithm is discussed in the paper in detail. We also then did the comparison of the two chunks of the two 3 day long periods on the same channel, one with algorithm, one without algorithm. And we see that almost 37% of the good viewers do not experience any kind of loss chunk rate. Overall loss chunk rate also decreased from 24.7% to 13%. We also tried to measure if there was any impact on the quality of experience for the viewers, and we do not find any quality of experience impact on the system, which is discussed also in more detail. We have also discussed in detail the experiments done in the testbed, which is present in the paper. Thank you very much, and thank you for your time.